So good morning, everyone. We shall start now. So we are starting the new module and the last module of this course, that is on additive manufacturing. So additive manufacturing is kind of a relatively new set of technologies which are used to realize products. So these are fundamentally different than the technologies that we have discussed up to this point. So, additive manufacturing is actually a subset in the set of technologies which are also known as rapid prototyping. So, there is this term which has to be understood first, that is about the rapid prototyping. So, what is rapid prototyping? So, rapid prototyping, it is basically a method which was developed in the late 1970s in order to develop prototypes of the new products. So especially this rapid prototyping is useful whenever you are developing any new product and which is not already existing. Uh, the concept may be entirely new, but we want to test that product. So we developed this set of technologies to quickly realize that prototype. So prototype, it is a beta version of any product, like there are beta versions of the softwares. So a prototype, it is like a beta version of any product which is initially developed to see the functionality, then to give it as samples to several customers to get their feedback in order to improve the prototype. And once we have sufficiently improved the prototype, we send it for mass production to develop new products. And it is after this mass production stage the product finally enters the market. So rapid here basically implies that we want this prototype to be ready in the shortest possible time. Now what happens in conventional the manufacturing processes that we have discussed? So there is a series of flow, that is we have a set of primary manufacturing processes, then we have secondary manufacturing processes. Okay, so what happens for any material to develop any product from any material? The material has to undergo these set of first the primary processes, then it has to undergo the secondary processes. It is after it is subjected to number of these processes. So under primary we have studied about casting and forming. In secondary we have studied about joining and machining. Of course, there are other processes which improve the surface. There are surface treatment processes. There are processes like heat treatment which improve the microstructure of any product. But you see, to basically accomplish all these processes, what has to be done is basically you need to invest time. So this makes this conventional route a time consuming route. So just to overcome these steps of different processes, rapid prototyping, this makes the product in, we can say, in the same process, in one shot or in one step, the product can be ready. So that is why they are clubbed as rapid. So this is the meaning of the word rapid here. That in one step, perhaps you can make the product. You don't need to separately do the casting, or you do not need separately forming, then machining or joining. Perhaps in the single go, you can make the product. But the downside of these processes is that they are not suitable for mass production. Although the technology has now significantly improved over the years, but nevertheless, still the additive manufacturing or these rapid prototyping technologies, they are not suitable for mass production. So that was the intent, basically to study the earlier processes, and now this is the intent to study about the additive manufacturing. So additive manufacturing is not only restricted, I can say, only to mechanical, but it is now widespread. It is used in civil engineering, it is used in biomedical engineering, even people in electronics and all, they also use this additive manufacturing and the processes associated in this. So it is a very interdisciplinary topic. So we will in this basically module, since it is a level 1 module, I will just try to give you an overview about this topic. So this is just you can see say tip of the iceberg, but it is a very vast and very interesting topic. So I will just leave you by giving the overview with some insights about the different processes in additive manufacturing. Perhaps one or two processes we will see in detail, and then perhaps and that is from the course perspective that will complete it. But you are always if you are interested, you can always definitely explore this type of process. Very useful to develop different products. So with this brief introduction about additive manufacturing, we jump into the contents of this module. So you see these type of products. So these type of products essentially they do not I can say follow a particular geometrical shape. So they cannot be quantified as a definite geometrical shape, because inherently these are very complex shapes which cannot be even modeled by complex mathematical equations. So essentially, in this case, our existing product realization technologies like machining, casting, or forming may not be very suitable to develop these type of products. But inherently, we have a need of these type of products, like this robot. So robotics is there, or this robotic arm is there. Similarly, this type of the skull patch is there, which has to be developed. This is the basically the section of a spine bone. This is the femur bone. So you can see that this is the skull patch. That these products that I'm showing here are basically very complex products, and if these products have to be made, so these products have to be made specific. If I leave this robotic aside, all these products that I'm showing here, these are again specific to a person. Perhaps we cannot generalize the shape of a spine bone or a skull patch. It is very specific to a person. So the advancement in the biomedical field in these days has enabled us to even develop these type of products by using one of the additive manufacturing process. Similarly, there are also products beyond the biomedical domain, which include this type of lightweight bikes. Then these prosthetic limbs are there, and of course, these are always not restricted to plastics or polymers, but we can also make products which are metallic products. These these gas turbines, products of these gas turbines are there. So all these products, these are gas turbine components. So gas turbines are the components basically used to generate power by burning natural gas. So all the jet engines used in aircraft, they work on this principle of gas turbines. So these type of products which have a very complex geometry, but at the same time, we may not require them to be produced in large varieties, are very suitable to be produced using one of the additive manufacturing process. Okay, so talking of the specific definition of additive manufacturing. So additive manufacturing is basically an appropriate name to describe technologies which make products, especially three-dimensional products, by adding layer by layer. Now, this is the main highlight of all the additive manufacturing uh, technologies, that in this technologies the product is built layer by layer. So we have discussed about machining processes in the previous module, in which the excess material was removed layer by layer, so that process made it a subtractive process. But additive manufacturing, it is an additive process, as the name itself is indicating. So what we do here is we basically add this layer by layer of the material, and we keep on adding the layers of the material, thereby making the final product. So this is the main difference between additive manufactured products, that they are built in a layer by layer fashion, and products built by the conventional set of manufacturing processes that we have discussed. Now, if I talk of materials which can be AM'd or additively manufactured, so I am using this additive manufacturing as AM, so I'll be using AM in the subsequent slides. So the different materials that can be AM'd or additively manufactured include everything. So this even includes materials beyond the conventional regime of these plastic, metal, ceramics, or composites, even to concrete and human tissue. So you can see that additive manufacturing has progressed in a very exponential manner, and as on date, all these materials are possible to be products made out of all these materials are possible using one of the additive manufacturing technology. Moving ahead, additive manufacturing technologies, now since we are discussing about the different capabilities of these technologies, the requirement of this technology is fundamentally different than the conventional manufacturing processes. So what we have studied in the conventional manufacturing process, so in conventional manufacturing process, essentially you need a equipment, for example, of welding. So there you need a welding setup, which may be an arc welding setup or it can be a gas welding setup. Then perhaps you need a workpiece, of course, which has to be joined. And then basically you need an operator which will do the welding and join the workpiece. But if we look in additive manufacturing, the difference here comes. The first difference here is, instead of directly needing a only in hardware, so all the additive manufacturing technologies, they essentially need a three-dimensional modeling software. This is a most important, I can say, starting point for any additive manufacturing process. So three-dimensional modeling software, it is also known as Cad software. So CAD, what is CAD? CAD is computer aided design or drawing. Means there are specific softwares which allow us to create three-dimensional models of the products using this computer software. Now, this is the first step for any additive manufacturing process. For any product that you intend to develop or make, most important part is that you should be able to first make the three-dimensional model of that product in a solid modeling software. So one of the example of the software that is used is SolidWorks. So SolidWorks, it is a proprietary software, and in this regard, basically we have to uh, use this with specific license. But again, there may be some open source softwares also available to do this type of modeling. Then next important step which comes in additive manufacturing is the equipment. So this is similar to as the equipment I discussed, like the welding equipment is there, like the welding arc welding setup is there, or the gas welding setup is there. Similarly, in additive manufacturing, we need a equipment which will do this additive manufacturing. So this can be a 3D printer or it can be a SLS machine. So what is SLS here? So SLS is selective laser sintering. So selective laser sintering, it is a process to develop additive manufactured parts. Typically, it is used for metallic parts. So we will see more details in the subsequent slide. But as of now, what is important to understand, to do this additive manufacturing, first step is to have a 3D modeled software in which you can develop the solid model of the product. Then you need a machine which will do the additive manufacturing. And lastly, you need the layering material. Here we don't need any workpiece, okay? We don't need any stock, because the raw material itself will be converted into the product. So the layering material, it can be any material. It can be a plastic like ABS, it can be metal, it can be ceramic. So layering material, it is the material of which the product will be made. Suppose you want to make a product of plastic, so you can use ABS. So or it can be of metal, it can be of ceramic. Now this layering material, it is available in different formats. So layering material is available either in the form of filament roll, okay. It can be available in the format of a powder. So these are two popular formats or the forms in which this layering material is available. Typically, this filament roll is popular with plastics, okay, or it is popular with polymer matrix composites. And powder is more popular with metals and ceramics. So now these three things are most important to do any additive manufacturing process. So moving ahead, we will see the names of the technologies, which are some of the technologies which are in this umbrella of additive manufacturing. Okay. So there are different technologies which come in this category of additive manufacturing. So one of the technology is 3D printing. So 3D printing, you might have also heard about this technology. It's very popular these days. 3D printing is one of the technology, also abbreviated as 3DP. Then we have the rapid prototyping. So rapid prototyping is also a broad name given to all these technologies, and rapid prototyping is also specifically sometimes referred to as one of the additive manufacturing process. Then SLS is the selective laser sintering. I have already discussed regarding this. Then another technology is fused deposition modeling, FDM. Electron beam melting, EBM is there. Then is layered manufacturing and additive fabrication. So these are some other technologies. So again, coming to the scope of this module, we will be discussing in detail only about this 3D printing and the fused deposition modeling. Other technologies, they require more detailed discussions, and perhaps at this stage, these are out beyond the scope of this course. Okay. Now, another important aspect of these technologies is they are what you see is what you build type of technologies. So, what I mean by this is that all these technologies basically work on this principle that whatever we are able to see in the 3D model. So, here C is in the three-dimensional model, whatever we have created, the same will be replicated when the final product is prepared. So this makes it what you see is what you built processes. Okay. Now we will look at a generic process chart to make any product using any additive manufacturing process. So generally if we want to make any product, they follow these 8 steps. So these 8 steps will be same regardless of the material which is there, regardless of the product which is used, regardless of the technology under additive manufacturing you pick. So the fundamentals of this will not change. Only the material will change or the technology will change, but the steps they remain the same. So we will discuss these 8 steps now. So step number 1. So here we are taking the example to make a coffee mug. Okay. Suppose you want to make this coffee mug. So this is the final objective, for example, in this case. So step number 1 is to develop the CAD model that I have discussed. So using any three-dimensional solid modeling software, you will first develop the CAD model of this coffee mug. So this is step number 1. Step number 2 is to convert this CAD model into STL format. So this is very important to understand what is STL format. So STL here stands for stereolithography format. Stereolithography is actually one of the additive manufacturing process which was initially developed. So since it was initially developed, so all the files which were needed to do this process were saved as .stl. So we have seen that computer can save the file in different formats, like you save in doc, you save the file in PDF, or you save the file in some other format. Similarly, what you do is while you create this solid model in the Cad software, the same software also enables you to save that Cad model in the format of STL, which stands for stereolithography file. So that is the full form of this STL. So once you save it in the STL format, so what it does is basically in the STL format, what is being done, the CAD model is split into slices because the product will be made in a layer by layer fashion. So STL file is basically splitting up into slices which can be processed as a single layer. Now, why we have to convert into STL file, that I will explain in the next step. So once you convert into the STL file, you transfer this file to the machine. Now this machine here, what is indicating is the machine which will do the additive manufacturing. Now this machine can be a 3D printer, it can be an fused deposition modeling machine, it can be a selective laser melting machine, it can be a electron beam melting machine or layer manufacturing machine. So machine here stands for additive manufacturing equipment. Okay. So this additive manufacturing equipment is termed as machine here. So once this STL file goes to the machine, now this machine can only understand the STL file. Okay. So the machine cannot understand the CAD file. The machine has that limitation. So that is the need to convert the STL file, the CAD file into the STL format. So file transfer, whatever is done, it is done in only in the STL format. So file transfer can be done over the local area network, or it can be done using a pen drive, or these are the different methods by which you can do. Then once the file reaches the machine is set up with some initial parameters, reference setting and all is done in the software which is provided in the machine. So generally these machines are coupled with a computer. So all the softwares are installed in the computer in which you initialize the parameters to do the additive manufacturing. Of course, I am not discussing about those parameters as of now. So once the parameters are set, you give the command to the machine to build. So build means now the actual manufacturing has started of the product in the machine. So the machine houses the platform where the product will be made, and it will be again made layer by layer. So this build part will be done in a layer by layer fashion. So that is the characteristic of all the additive manufacturing processes. So this build which is being done in the machine is typically unsupervised. Means once you have given the command to the machine to make the product, so generally no operator is needed to do any change in settings for that machine. So it can do unsupervised, and it will go on building the product until it has completed the product in the final shape. So that may take, typically depending on the complexity of the product, it may take a few hours to few days to few weeks. So in a way, additive manufacturing for complex parts is slow, but what happens since you eliminate all the primary and secondary processes, the process becomes relatively rapid. So build can take from few hours to few days to few weeks depending on the size and complexity of the product. So once the product is complete, the machine will give an indication, and now the product here in stage number 6 is ready to be removed from the machine or the additive manufacturing equipment. So once it is removed, there may be some post processing required, like cleaning may be required, or in case of metals, sometimes heat treatment is required to further improve the properties. And once the post processing is complete, the product is ready for use. So as shown here, the coffee mug is ready for use. So what we have done is, typically we started with this CAD model and we have completed it with the final product. So it is what you see is what you build, kind of a process. And essentially what you have seen, we have eliminated all the in between, all the needs of joining or casting or machining. So you can imagine, if you want to make a similar cup using a conventional machining processes, first you will need a block of this material. For example, if this material is I can say if it is a steel, so you need a block. Then perhaps you will need uh, basically some machining processes. Then you will also separately make the handle and you will do some joining processes. So essentially all those processes have got eliminated in this simple example of a coffee mug. So that is the beauty of these additive manufacturing processes, and I hope these 8 steps are clear to all of you, because these 8 steps will remain same regardless of the material, regardless of the technology which is used to do this additive manufacturing. Next, we look at the evolution of this additive manufacturing, or some historical aspect of this additive manufacturing processes. So additive manufacturing processes, they are relatively new. They were started in the late 1970s and 80s with the rapid prototyping in 1988. Then they went on to rapid casting. So rapid casting here is here the intent was to develop the sand molds using this one. So all the sand molds that we discussed earlier in the casting, they were also made using this rapid casting process, which was under the additive manufacturing in 1994. Then rapid tooling was developed in 1995. Then in the new in the 2001, so additive manufacturing was first used for automobile components. So different automobile components were made using additive manufacturing. Then in 2004, the additive manufacturing was further expanded to aerospace, and in both these cases, it was limited only to polymers, because at that time we did not have the proper equipment to do the additive manufacturing for metals or ceramics. Then again, for biomedical equipment, different polymers, jigs and fixtures were developed in 2005. And implants, so with the metals, we started to play with metals in additive manufacturing only, I can say, 10 or 11 years back, in the form of implants. So medical implants are basically the used as products for bone application, especially in knee joints and all. Then, since we gained expertise with metals, it was expanded for aerospace with metals. Please remember, earlier the aerospace was restricted only to polymers. In 2011, 10 years back, it was expanded to metals. Then in 2016, it entered the nano manufacturing regime. So nano manufacturing is the regime where the parts which are produced is of the order of few nanometers. So such products, they find application in micro. You might have heard about these devices, micro electromechanical systems, MEMS devices used in actuators and all for spacecraft or undersea exploration or mining and all. So MEMS is basically micro electromechanical systems. Then in 2017, the additive manufacturing was expanded to architecture, and this was primarily for building homes. So China was the country which uh, used additive manufacturing to make homes. Okay, so these are very rapidly produced buildings. Then, of course, for biomedical implants and scaffolds, then in situ biomanufacturing, that is basically the future projection of this technology. And by the end of 2030, we expect the additive manufacturing can even make the full body organs like heart, kidney, and all. Even presently, also there are several reports in which a full heart or kidney is being manufactured using additive manufacturing. So you can see this technology is very widely expanding, and it is influencing almost all spheres of our life. So that makes it very important to read about this further. So if I summarize the some benefits of additive manufacturing, so this basically provides increased design freedom compared to the conventional casting and machining. So almost the existing design rules they do not limit this process, so you can virtually make any type of a product using this additive manufacturing. With additive manufacturing, of course, we can make lightweight structures which are having high strength. We can make complex internal features like internal channels which may be built in one stage. If you have to do these complex internal channels in conventional manufacturing route, perhaps you will need a separate machining process to develop these type of channels, which makes it a complex choice. Then net shape processes. So net shape is a very important aspect of manufacturing, where we want the product to be developed in the final shape with minimum processing. Minimum processing means that we want that minimum material should be wasted in developing the final shape. So that makes the word net shape. Net is what we require finally. So in conventional processes, especially with machining, so you have understood that lot of material gets wasted in form of small chips. But that is not the case with additive manufacturing, as no chips are produced in this regard. So this may save up to 25% less, 25 times less material as compared to machining. So net shape also reduces further operations like assembly operations, which include welding or brazing. So you can look at back at the example of the coffee mug. So the handle of that coffee mug was built into that product. We did not make the handle separately and then join it with any separate process. Then we may not also need different tools like we have studied in the machining processes, that you need a cutting tool which should be harder than the workpiece. But in case of additive manufacturing as such, we do not need any such tools in this case. Then of course the production cycle time. So production cycle time is basically the total time taken to develop the from the raw material to the finished product. So it is quite short compared to the conventional manufacturing route. Then total cycle time, they may be done in several days or weeks. Generally, it is quite shorter than the conventional manufacturing processes, which spans over several months. And additive manufacturing is always, as of now, recommended only for small series. So that is one of the limitation, that additive manufacturing is not suitable for mass production. So looking at the benefits, we also need to understand currently what are the limitations of the additive manufacturing. So why I am saying currently, because the technology is evolving very rapidly. I am talking today of some limitations, maybe in 6 months that limitation goes away. So we are just looking in the current limitations of this technology. So as of now, the technology can develop efficiently develop parts of the range of 250 to 250 square cubic millimeters, which may have expanded say up to 500 cubic millimeters over past 6 months and so or so. Due to low thickness of the powder layers, so process may be quite costly. Now, why this is important to understand? Because I mentioned that the raw material which is used in additive manufacturing, it is either available in form of filament, okay, filament roll, or it is available in the form of powder. Now there is a cost which goes into producing these filament roll or powder. So the raw material which is used in case of additive manufacturing is essentially it entails certain cost. So that makes overall cost of the product slightly or sometimes significantly higher than the products which are made using conventional processes. So producing this raw material is a costly process which adds to the cost of the additive manufactured parts. Then process is not suitable for mass production, that I have been discussing. So it is still the technology cannot handle a large number of parts, which is still only possible with conventional manufacturing processes. Then parts may need support structures where the overhang angle is below 45 degrees. As such, we are not using in this case any jigs or fixtures. So suppose this type of product has to be made where you have an overhang. So overhang means you have a support here, but here there is no support. So in such case, you need to provide additional support material in this case to basically prevent this overhang from falling. So this is just the design limitation to some extent. Material choices, although I have mentioned all the materials, about all the materials like plastics, ceramics or metals are possible. But if we look into more details like which plastics, or specifically speaking of which metals, for example, super alloys, We have discussed about super alloys, which are metallic alloys which retain their strength and hardness at elevated temperature. They can still not be manufactured using additive manufacturing. So although we say all the materials, but still it does not encompass each and every material. Then next, very important, I can say, limitation of this process is inherent anisotropy. Please try to understand this anisotropy very carefully, what this is. So anisotropy is around the build axis. So what this means is, suppose you are making the part in the layer by layer fashion here. So you are adding different layers. Now this is a part made by additive manufacturing, and this is a part, say, made by casting. So in casting you will not have any layers, and in additive manufacturing you will have layers. Now there is a term isotropy, and there is an antonym of this term which is known as anisotropy. So isotropy is basically the property of any product or any material to exhibit same properties in all directions. Same properties. So these properties can be any properties. This can be mechanical properties in terms of strength, hardness, toughness, or it can be electrical properties like electrical resistance, conductivity, or it can be optical properties, it can be magnetic properties. So isotropic materials generally they exhibit same properties in all the directions, all directions. Okay. All directions means principally I am talking of three axes, that is X, Y, and Z. So products which are made using the conventional manufacturing processes like casting, machining, welding, and all, they exhibit isotropy. So this means the property of this product is same if in all three axes. If I take these three axes, Z, Y, X, and Y, so properties are same. Means I take sample from anywhere, I will have the same or similar properties. But what happens in additive manufacturing? So additive manufacturing, we are discussing that the product is made in a layer by layer fashion. So product is built in this fashion. So what happens where these two layers they interface, where these two layers are interfacing, there inherently there is a discontinuity. Okay, so there is a discontinuity where the two layers are interfacing. So at that point, the properties are not same. So the properties they differ than properties what is there inside the layer. So properties at the interface, at the interface and at the inside the layer are different. So this gives an anisotropy, especially in the build direction. So layers are only experienced, suppose in the Z direction, in the X. So if this product is like this, so you are only able to see the layers in the thickness, or across the thickness. If you look in the Y, so this is the Y axis and this is the X axis. So in the X and Y, perhaps there are no layers. So property in one plane is same, but if you vary the axis along the thickness because of these layers inherent discontinuity, the properties differ. So this property, where these properties differ in the specific direction, so properties are not same in all directions. For additive manufacturing, this is not same. So this is known as anisotropy in additive manufacturing. So this is a major limitation to some extent in additive manufacturing, and still we are able to not able to find appropriate solution to this limitation of additive manufacturing. Next, I'll say about the densities. So densities of the product in additive manufacturing cannot reach theoretical density. So theoretical density is the density that you calculate using the theoretical basic formula that you have been reading in school. Density is mass upon volume. But in additive manufacturing, the densities may be up to a max of 99.9% of the theoretical density. So this is theoretical density. So why this is not 100%? Because of this discontinuity, there may be certain pores which may be left. So in all cases, all in all, I can say it is not equal to the theoretical density. So that is another limitation of additive manufactured parts. And because of these different densities and anisotropy, so the mechanical properties of additive manufactured parts sometimes they may be inferior to parts which are wrought or which are cast. So that is the some of the limitations of this additive manufacturing. So next is different industries which use additive manufacturing as of now and maybe in future. So these include aerospace, dental implants, automobiles, jewelry, then again biomedical implants, surgical devices, textiles, prosthetics, furniture, food, electronics, sport equipment, toys, etc., armaments, tool making, mold making, and all. So you will see practically additive manufacturing touches every industry in some way or the other. So these are the some of the scopes where the additive manufacturing can be used. Of course, the scope is expanding with every passing day also. So with this, I will stop for today and have some. We can now have some discussion or questions from your end.